This video is the part 3 of the XPS fitting course using KherveFitting. So in the part 1 and part 2 we have fitted the carbon 1s using 4 picks with this C1S1, and we have fitted for the samples we are studying. We have fitted one with 3 picks. We also have done the binding energy corrections, and we have saved the data into the picks library. So now we will turn into the real sample, because the carbon 1s here is only used for the binding energy corrections. And we have the oxygen 1s and we have the Mn2p. The Mn2p. So the oxygen 1s, we would first look at where the oxygen 1s should be for an Mn oxide. So I call this one the MnO2, but it may be an Mn2O3 or MnO, I do not know. So I would look first into the NIST, and here I have the NIST XPS. I've got it open already here. So I will go into it. Actually, just reopen it again. This XPS, and I turn to go into the spectral, and then I would go into the oxygen, and in the oxygen you would see two things. The first one is in the thermofisher. In the XPS simplified, you'll find that the metal oxide peak is below 530. And then you have the organics, the C single bond O and C double bond O, which we have. We've seen it in the carbon 1s. Should be around 531 to 533. Please note that this should be the, this is the C double bond O, and this is the C single bond O. Okay, so it goes towards high binding energy for a C single bond O, and then low binding energy for a C double bond O. So it's the opposite way. And then when we look at the oxygen 1s in here, we look at the oxygen 1s, and then we are going to choose the Mn. And we, for example, we are going to start with the MnO. And the MnO, we get the MnO2, MnO, and the MnO is all less than 530. And the MnO2 is also less than 530. And if we choose the Mn2O3, it's also less than 530. So we expect the lattice peak, the oxygen lattice peak of the Mn oxide, to be less than 530. And yes, we have one, but we do not expect to have a peak here. And this is the peak from maybe the Mn, the CO, which I believe it is. So let's start the peak fitting. Also, when you fit oxygen, it is not as straightforward as it is as carbon 1s, because there are too many peaks that are shown here, and it may just look like one peak at the end. So it's hard to differentiate. What we can know is the lattice peak. So now we are going to create our background, and if we go again, control down, we can see that it's well fitted. We may actually just go here and then shift and use this, and the same for the oxide. So shift, and this is good. So we go back to zoom out, and now we are going to go into our peak fit, and we are going to use, now that we got used to the void, we go into the void, and we are going to use one peak for now, another peak, and we are going to use the tab button to move this one around there. And then we can see that there is something here. So if we let it fit with 2 peaks, because it looks like there may just be 2 peaks, what we see is it creates a big, very broad peak, which is kind of meaningless because you cannot have such a broad peak. So it's around 2.47 and this one is 1.4, and we've seen with our carbon 1s before, this was around 1.6. So I do expect peaks to be around at 1.6. So this, I do believe it's not correct. So I will start first by varying this number. And I will also change this value because that should not be Gaussian, that should be 20%. So I will allow him to stay around there. So for a void function, I tend not to fix because currently it doesn't work too well. So I only put a slight variation like this, and I will make the LG ratio of the second peak the same shape. Okay, and then now I can see that because this one tends to be much bigger, then there must be a third peak. Let's try first as putting the same width. So the width of this peak is controlled by the width of the Gaussian. And then because of the LG ratio, the width of the Lorentzian is recalculated. And now you can see that there may be a third peak here. So this is actually the location for an oxide, OH. And that's what we, hydroxide species, sorry. So that's a peak that is tend to be broader, but we will give him the same shape because there's hardly any reasons to be different. But okay, we may change that and go to something between 10 and 20. And we will let vary the width, the main width. And now you can see that actually we get something close to 1.6, which is again the same as what we had for carbon 1s. Okay? So it's all in line to what we think. So now we fit this second time, and that we may disagree, because now you can see that for oxygen it's very difficult to get something trustable. So I will tend to put it somewhere around here, and again that's too much, so I will avoid it to vary to that level. So 2.3 is a bit too much, so I may go something like 2. Sorry, 1.5 of Gaussians. That should give something 1.8 maybe. And now it starts making more sense. It's still not perfect, but this is a good start. And from this now you can see that actually the LG ratio of 19.9 is too much. So that may want to go to something like maybe let's try between 10, because it's still 1.6, 10 to 20. And then the ratio of the next peak should be, because it's broader, so it should be also 10 to 20, not going to 20%. So let's make it the same width now, the same shape. Now you can see that here he wants to go broader than what it is. And he's stuck at 1.5, which we did. So now we are going to slowly go up. And I would tend to take it actually and see if I can maybe fix it to this value. And let's see how it looks when you go up. So that's actually not too good. I'll give a different position, maybe plus minus 0.3, let it vary a tiny bit. Maybe it's still going to the maximum, to the minimum, and maybe actually 0.3 again. So it's varying and varying. maybe that's something that looks quite good. Yeah. Okay, so now with this, let's name them. So that may be, to my view, this is the oxygen lattice from the MnOx. I do not know what species that is. And this is 531.5. If I look at the value from the XPS simplified, I can see that 531.5 should be the, I call it O double bond C and the O single bond C. I tend to change the name so that oxygen is the reference because we are looking at at oxygen. Okay, that's it. So this is how I would do the oxygen, and then if I look at the manganese now, the manganese looks like this. The manganese is made of multiplets, so it's not just a single peak, it's several peaks, and for that you would have to look at the Bissinger. So again, I would go into the knowledge and look at the XPS fitting from Bissinger. Okay, so this is quite difficult, so it's hard to see now, but it is made of several multiplets, with the main peak shown here and then several multiplets. So that's for the Mn2O3. The MnO is even more multiplets, and there is a shake-up satellite, and this is the Mn metal. So it's not something that for beginners you want to fit. So there's another way you can use. You don't need to pick fit. You look at the shape of the peak, and for now, when we simply look at if you look at MnO, and maybe actually the one from the XPS simplified is easier to see. So when you look at those shape, let me just try to put that nicely. So in the shape, we don't seem to have a satellite. So to me, the MnO is out of the characteristic, and it may be an MnO2 or it may be an Mn2O3. But the MnO2 would tend to have some kind of double peak at the top, and that's not something you see. So it is more likely to be Mn2O3. And then there is the peak position. But in that case, the peak position is very confusing, because if you can see the peak position in here, this is 642.8, and 642.8 in the XPS simplified is not even seen. When you go through the NIST, which is here, then you may find that for the MnO, MnO2, it can go up to 642. So now you've seen that sometimes the XPS simplified is not quite correct. So going on verifying it in the NIST, but that seems to go between 641.6 to up to 642.8. So there's one EV difference, and that may be the same when you go for MnO2O3. It goes 641.6, 642, and okay, so that seems to be less, 642.8 here. So it is possible that it is any of them, but it is more likely to be, for now, Mn2O3. And then in here we are just going to quantify now the amount of Mn species, and we are going to compare it with the oxygen species. So for that, we don't need to pick fit, we can measure the area. And there is this button there. So this one is a blue type background, and this one here is a yellow background, just to differentiate, because they look kind of the same. So in here we do exactly the same as the other one. So we create a line, and then we create the background. So that's how the background is created, and then we name the area we want to measure, and now we can measure anywhere around there using again the line. So we're just going to fit the line. And if you don't have access to the line, you can just reset the vertical line and just put it as you like. The reason you can do it like this is because I can decide to just measure from here to there, and it will not take the area of those two locations. In this case, I want the whole lot, so I will just take around there, and I calculate the area, and there for now is my area. So this is my uncorrected area, this is my measured area from the intensity. And now I can simply export the area results into the results grid. But for that I also have to check something. I have to check if I have the right library. So I have measured this with my thermal machine, and I will go into the preference, which is here, and in the preference there is instrument setting. And in instrument setting I need to make sure that the ECF method, the energy correction factor method, is the TPP2M. This seems to be the best method. There are other methods available, the Schofield, the Wagner, but the TPP2M is the best. So I would tell you to just use that one. And then for the instruments, I've used a K alpha. So I would go in here and I will use the AL K alpha. So this is the one here, AL thermal 1, and if you use the Kratos, you have the choice down at the bottom. If you use the phi, it's all there. The A is because it's the sensitivity factor from the Advantage software, and the C is the sensitivity factor from the CASA software. Okay, so I trust the one from the Advantage because it was taken with this machine, and I save it, and you see where the binding energy correction settings are, by the way. Now I save it, and if I export this, I get my area, and then my corrected area is just here. This is my atomic concentration at the moment, and if I just check it, it's 100%. And the RSF that was given, transmission function is always 1, because that's done in the Excel page. Okay, but then all the settings are shown here. So now we go back to the oxygen, and we can do the same. So now we are going to export it there, and then we can just tick and just check what we would expect. So the results here show us a 2:3 ratio, which is what we would expect if it was an Mn2o3. So already now we have proven that the shape was looking like an Mn2o3, and the quantification was showing Mn2o3. So this is how you would do it. If by any chance you are more of an advanced users, you can also use the recently made peak library from the Bissinger paper, and I will just remove those values again. So I remove the whole lot, and then we will use the library of the Mn2o3. So for that, again, we create a background, and then we can go now into the peaks library, go into the Bissinger folder, and for example choose the Mn2o3, which is provided in this paper. So that would be, and for now I will leave it like this, that would be the one, if I go in here, that would be the one providing those peaks. And they are somewhere on, I think they are in this page, they are somewhere in there, all these peak tables. So if you click on it, you get the numbers, and this was recorded as a peak library. So now let's just move the peak. To move the peak, by the way, you have to be on it. If I type on tab, you cannot move it in there. You have to go into the peak fitting tab. So I have to go in here, and now if I press tab, I have access to the A, and all those peaks are in function of A, even in area. So that means that if I put that up, then they come up. And this is the peak table from Bissinger, and you can see that it more or less fit. Obviously there will be a slight change. This is done at 1.75. We've seen that the resolution was quite poor, so maybe that whole thing will need to be at slightly more wider width. Okay, and also it's a Gaussian library, so as you can see, if I just type A, the model is GL, just like on this paper, and that's why it's not fitting too well on the side there. So if I was to try another PIC library, for example the MNO, yeah, I'm doing exactly the same. Maybe let me go back to A, and then you'll see that it's not really fitting. So only the one from the Mn203 was really fitting. So that's again another proof that this was an Mn203. Okay, so that's the end for this part 3.